And so here we're looking at this standard hydrogen electrode and connecting it here. And so we have the oxidation potential plus the reduction potential. Now, the problem is we can measure the cell voltage. And I forgot the sheet. I left the sheet in the office. We can measure the cell voltage, but how much of that voltage is due to the anode and how much of that voltage is due to the cathode? In other words, how much is due to the oxidation, how much is due to the reduction? And so if this is a tug of war, you know, the permanganate and H plus are pulling the electron density over here, and it's H plus is resisting that, and then H2 is also resisting because it's going to cost energy to knock the electrons off H2 and break the bond. And so what we see here is this voltage is a composite of these two. But we run into the problem where
we don't know how much.
Yeah, we don't know, and therefore we're going to arbitrarily assign which one's 0. The hydrogen. And so the oxidation potential, which is going to be the hydrogen goes to H plus. This is it. Hydrogen goes to H plus is defined as 0 volts plus the reduction. And so basically this whole thing becomes the reduction potential, which introduces a systematic error in these. And so each of these alone isn't right. You know, is it really 0 volts to convert H2 into H plus? No, it isn't. And so that's going to introduce an error here. It's also going to introduce an error here, but one error is going to be too big, the other error is going to be too small, and when you add them up, they cancel each other. Yeah, and so that's the good thing about the systematic error here. They'll cancel each other out. And so as long as we add an oxidation potential to a reduction potential, that error cancels. And we have to do that because in order to have a redox reaction, you need to have both. You can't have oxidation and oxidation or reduction and reduction. You have to have oxidation and reduction. And so this is how we're going to measure potentials. We'll just leave the SHE here, that's 0, and then we'll just change this beaker over here. We'll try to put something new on here and see what it measures. And so the thing we're going to try next is this. Actually, does somebody have their chart, the redox handout chart?
Yeah.
From Piazza? What's the potential for this? The reduction potential for permanganate?
1.51.
1.51. And so this is permanganate goes to manganese 2 plus. So this is 0 volts. This is going to be 1.51 volts. And so the cell potential that we generate here under standard conditions is 1.51 volts, a composite of these two. All right. The next one we're going to put in here is zinc. Try that. When we put zinc over here at the cathode, we'll have zinc here, and what should be the oxidizer? I'm going to put in Zn2 plus as my oxidizer. The Zn2 plus is going to be 1 molar here. And so the reaction that should occur here is that Zn2 plus takes 2 electrons to form Zn solid. And so I'm going to just go ahead and add up the potentials here. The oxidation potential is 0 volts. And what is the reduction potential of zinc? Zn2 plus 2 electrons yields Zn solid. Okay, what is, on the chart, what is this one? Zn2 plus 2 electrons go to Zn solid.
It's negative 0.763.
763 volts. And so the total cell potential is negative 0.763 volts. Now, what does a negative voltage mean? A negative voltage means that the electrons aren't going left to right. The electrons are trying to go the opposite direction. Because now in this tug of war, who's stronger, Zn2 plus or H plus? H plus is the stronger oxidizer, so the electrons are trying to force their way backwards here. And so this reaction as written is actually wrong. When your voltmeter was wrong, what did you do? When you got a negative voltage, you just swapped it, right? And so what we need to do is we need to swap the beakers now. We got to put this beaker on the left and this beaker on the right. And so this is what you do. The voltmeter has a polarity. When you put the red and the black on there, you're saying that this is the cathode, that's the anode. That's what you're doing with the voltmeter. And if you have it backwards, then you're going to get a negative voltage. What you have to do is you have to swap the leads, right? And then give the red lead to whatever and the black lead to whatever to make sure it's right. And so that's what I've done here. I just have the leads on backwards because this is not right. You know what this should be? I should redo this. And so what we see is this is non-spontaneous as written. Because what we have here is this. A cell potential is what we call an absolute zero. When the cell potential is 0 volts, that means something. A cell potential of 0 volts means we have a completely dead battery. I.e., it's at equilibrium. Dead battery, though, we'll talk about that more. Dead battery can be, it's still live, but just has too low voltage. A cell potential that's greater than 0 volts means spontaneous. A cell potential that's less than 0 volts means the reverse reaction is spontaneous. And so this is just our convention. The reason I ask you to write the anode always on the left is that, we can see, oh, something's wrong here. We get a negative voltage. That means I must have assigned it wrong, right? And so what's going to happen is, well, we flip the meter, and then we end up with a positive voltage. Same exact setup. And so it's just the meter, we just connected it wrong. And so all we do is this. I'm going to redraw this correctly. What we should have had here is the zinc should have been over here in Zn2 plus. 1 molar. And this should be attached to the SHE. And we have some salt bridge. So if we do this, where we have H plus at 1 molar, which way are the electrons going to go? Electrons will go left to right. And so now it's properly assigned. This is the proper anode. This would be the proper cathode. Electrons flow left to right. Our voltmeter will be positive. And when we do this, now we have everything assigned correctly because the oxidation wasn't the hydrogen. As before, the oxidation now is the zinc. And so the oxidation potential is going to be zinc goes to Zn2 plus. This is a shorthand way of writing that. Plus the reduction now is H plus goes to hydrogen gas. This is also a shorthand way of writing it. And so zinc goes to Zn2 plus is now going to be plus, because this is an oxidation potential. Your chart just shows reduction potentials, but if we want the oxidation potential, we just reverse the reaction and change the sign. And so this will be plus point, what was it, 763 volts?
Yes.
Now this one, we just reverse the reaction and just change the sign. Actually, no, this one's as is, which is 0 volts. And so this comes out to plus 0.763 volts. And so do you see we just had the voltmeter on backwards? Does that make sense? Now it's right. Okay, so that means this. We have sign conventions for the electrodes. One of these electrodes has a positive sign. The other electrode has a negative sign, like on a battery. And so which one of those electrodes should have the positive sign?
Cathode?
The cathode? Yeah, the cathode is correct. This electrode is positive. And so your red lead on the voltmeter should go to the cathode. The black lead on the voltmeter should go to your anode, which has the negative sign. An easy way to remember this is at the anode, what's being generated? Electrons. Electrons are being generated because the reaction is zinc solid goes to Zn2 plus 2 electron. And so if electrons are being generated, then this electrode should be what charge? Negative. And the electrons are being fed to the cathode because what's at the cathode? We're consuming electrons at the cathode. And so the cathode is pulling in the electrons. Well, what can pull in the electrons? Positive. And so in a battery, let's say the positive terminal's up here, the negative terminal's down here. Which way do the electrons flow in a battery? Electrons are going to flow from the bottom to the top. It's kind of weird because, usually the positive you got to watch out, right? Well, thinking. The positive is the hot terminal, they call it. Right, but really the electrons are flowing this way. Being generated. All right, so once we have some of these voltages, we compile them in a table. And in the table, we see that fluorine has the highest reduction potential. This is called a reduction potential. It's under standard conditions, so we call them standard reduction potentials. What's the reduction potential for fluorine?
2.865.
2.865 volts. And so, is this a big number? Yes. This is the highest on the chart. Is there anything higher than this? Can you think of one thing that would be higher than this? Give me one reduction potential that's higher than fluorine. Well, it's not on the chart. You have to think of something. So can you think of one species that has a higher reduction potential than fluorine?
Can I take a guess?
Take a guess, yeah.
Okay, HCl?
No. Actually, H plus has a much lower. HCl, it's going to be the H plus. Chloride doesn't really want electrons. Reduction would be gaining electrons here. And so H plus has a much lower reduction potential. What is the reduction potential of H plus? You should know this one by memory. 0 volts. The lowest reduction potential on the chart is lithium plus. Lithium plus's reduction potential is going to be
Negative 3.04.
negative 3.04 volts. Now, does this negative sign mean that the reverse reaction is spontaneous?
Yeah.
The negative voltage means the reverse. The electrons want to flow the opposite way. Yes or no?
Yes.
You would say yes?
Would I be wrong?
You'd be wrong. It's no, because this zero is what we call an arbitrary zero, like degrees centigrade. The previous zero, the one I just erased there, is called an absolute zero. Right? And so what happens is this. The cell potential, when the cell potential is, this arbitrary zero cancels itself out in the cell potential. Because one's too high, the other's too low. But when you're looking at the individual cell potentials, the arbitrary zero does not cancel itself out, and so this negative is not meaningful. This negative just means it has a lower reduction potential than hydrogen ions. And so we're going to use this jargon. Earlier we used this. Fluorine we called the strongest OA. OA stands for, and lithium ion was the, no, lithium ion. Weakest OA. Now using Chem 1B, that would be more of Chem 1A. Using Chem 1B, we'd say the fluorine has the highest reduction potential. Lithium ion has the lowest reduction potential. And so if I ask you, give me something that has a higher reduction potential than fluorine, you're looking for something that's a stronger oxidizer than fluorine. Can you think of something that's a stronger oxidizer than fluorine?
Fluorine ion.
What, fluorine ion? Like fluoride? Would fluoride have a higher reduction potential than fluorine or a lower reduction potential than fluorine?
Lower.
Lower, much, much lower. In fact, fluoride would be off the charts. Fluoride would be worse than lithium ion. Fluoride would have a reduction potential less than negative 3.04 volts. Why? Because where does that extra electron go? That extra electron would go into the next shell, which is going to be totally unstable. Correct? So one electron will fill the shell, and then the next one, they have to go into the next higher energy shell, which is the n equals 3. And so that's good. You answered my second question. My second question is, what has a lower reduction potential than lithium ion? Well, fluoride would have a lower. Right? Because at least lithium ion can gain an electron and form lithium metal. Okay, but tell me something that would have a higher reduction potential than fluorine. The higher the reduction potential, the more likely it is to be reduced.
Okay, can I take a guess of like noble gases? Helium.
Helium? Helium wants electrons more than fluorine?
No.
So helium is going to have a higher reduction potential than fluorine?
No.
No.
I think I'm taking bad guesses.
No, that's a good guess, but just keep guessing. Not helium. Have you ever heard of an alpha particle? What's an alpha particle? An alpha particle is helium. Since we're talking about helium, I might as well add this. An alpha radiation, dangerous stuff? Why? Is it because it's highly radioactive? There's a radiological hazard with alpha particles? No, it's not because there's some kind of... Alpha particles don't emit X-rays or gamma rays or anything like that. What's so dangerous about alpha particles? The things that emit alpha particles, like plutonium. Plutonium is really dangerous because it emits alpha particles. It's the alpha emitter. Uranium, alpha emitter. Huh?
It's not because it's volatile.
Well, it's volatile in the sense that it's a gas. The gases are all pretty volatile. The liquids. And liquids, we usually use volatile for liquids vaporizing. You could use volatile for meaning violent. Yeah, it's violent. Alpha particles are violent because why?
Free radical.
It's not a free radical. It's even free radicals are reactive. Free radicals have dangling bonds. They want a bond, right? So free radicals, you want to avoid them. Unless you're trying to synthesize something, then free radicals will be good because you can make things. You can make new bonds, right? So I didn't really talk much about free radicals other than talking about photochemistry. And photochemistry is a good way to generate free radicals. There are other ways. What else?
They're unstable.
Yeah, why is an alpha particle so unstable? It has what? More electrons? No electrons. It has no electrons. Alpha particles are helium-2 plus. No electron. It's just the nucleus of a helium atom. The nucleus of a helium atom, do you think that's very stable? No, it's going to want electrons. So alpha particles have a much higher reduction potential than fluorine, and making them extremely powerful oxidizers, chemically very reactive. So inhaling alpha particles would be worse than inhaling fluorine gas, and you don't even want to inhale any fluorine gas, right? It is the damage it would cause. All right, so the higher the reduction potential, the better the oxidizer, the more likely it is to be reduced, right? Now, we only have one table here because we don't need another table. We just reverse the reaction. And so if I'm looking at oxidation potentials, what would have the highest oxidation potential? What does that mean? The highest oxidation potential means the species most likely to be oxidized or the species least likely to be oxidized? Most likely. And so what would have the highest oxidation potential on the chart? Lithium. Lithium would have the highest oxidation potential because it's the one species most likely to be oxidized. And what is the oxidation potential for lithium under standard conditions?
3.0.
Yeah, plus 3.04 volts. So that has a very high. What's the oxidation potential for hydrogen gas?
0.
0. Does that mean it costs you no energy to oxidize hydrogen?
No.
No, it's just an arbitrary
0.
0. And then the lowest would be not lithium plus, sorry. The lowest would be fluoride. Fluoride would be the most difficult to oxidize on this list, and that would be negative 2.865 volt. And so what we do is we just add the two potentials. The higher the oxidation potential, great. The higher the reduction potential, great. That's going to make a higher cell potential, more voltage in your battery, right? The higher the cell potential, the greater the driving force for the reaction. And so this is why I don't like... Did I talk about the equation that Petrucci has in his book? The equation that Petrucci uses in his book looks like this. I talked about in the morning class. He doesn't set it up like this. What he does is he does this. He says that E of the cell is equal to E naught reduction minus E naught oxidation. Something like that. Wait, no. Sorry, not like that. He does this. E naught reduction minus E naught reduction. What does that mean? why do you think he writes the equation like this? The reason why he writes the equation like this is because our table consists of reduction potentials. And you can't have a reduction and a reduction. You have to have a reduction plus a oxidation. And so what the equation is doing is it's converting one of the reductions into a oxidation. Does that make sense? And so this is the anode. Here, this is his cathode. But it doesn't make sense because intuitively, if somebody were to ask you this, if the oxidation potential is high and the reduction potential is high, then do you expect a large cell voltage or a small cell voltage? If the oxidation potential is high and the reduction potential is high, do you expect a small voltage or a large voltage? Large. You expect a large voltage. Why? Because both of those potentials are high. That means the reaction has a lot of driving force. That means the cell voltage should be high. Whereas if you left the equation like this, it's harder to think in terms of that because you're thinking, if it's more negative, then it's going to be more positive, and you're switching signs. And we don't want to switch signs. We want to do that all already. And so what I do here is when we do the oxidation, we automatically reverse it, thinking in terms of oxidation rather than reduction. And then we just add it up. High potential means high potential. High potential always means the same thing. High potential always means that there's good driving force for that to occur. And so you want the bigger numbers. High potential, low potential. Is this really low? No, there's even lower, right? But lower potential. But is the sign relevant? Because this is oxidation potential, and so when we switch the sign, does it all of a sudden reverse to reduction potential? No, because this is arbitrary zero. And so this is the point I was trying to make earlier. When you go from positive 10 degrees Celsius to negative 10 degrees Celsius, did the universe just reverse itself? No. Are the clocks still going clockwise? Yes. And so nothing happened here. This negative is just totally means nothing physically, right? Unless you're on the absolute. And so this would be like Celsius, that would be like Fahrenheit, and the cell potential would be like Kelvin. Right? The cell potential, the zero does mean something, and the positive and negative do mean something. So that's what we have. So I want to show you something called a cell diagram. The cell diagram is shorthand representation of the cell. I don't know, shorthand, one word or two words? One word. Well, a cell diagram, isn't that what we've been drawing? These beakers and stuff like this, and the electrodes sticking in here, and the salt bridge. Is this a cell diagram? Technically not, and so we have to name this something. What should we name this? This is not a cell diagram. We need to name it, but there's no proper name for this. So I call this a cell schematic drawing. Something like that. Schematic or cell drawing.
Is that your name for it?
That's my name for it. Because there's no Petrucci name for it. It's just a sketch of the cell. Sketch. Okay, what a cell diagram is something a little different. A cell diagram is a very compact way of representing that. And so for the first cell we built, we started off with zinc as the anode, right? And we list out how this is going to react. And so we draw this vertical line, we go from zinc solid to Zn2 plus. And then we do double bar, and then we go from, what was the oxidizer? Permanganate? No, we did copper, right? Copper first. And so we go copper 2 plus to copper solid. This would be the cathode. And so what the double line here represents is the salt bridge. And the single lines separate phase. Phase would be solid from AQ. This is a phase boundary, call it. And so this would be our first one. And we could calculate the potential for this one. What is the cell voltage? Well, the cell voltage under standard conditions is equal to E of the anode plus E of the cathode. And so we could just look at the anode potential. Well, that's E of oxidation. The cathode potential is E naught for reduction. To prevent any mix-up, we can use the shorthand here. The oxidation is going to be E naught for zinc goes to Zn2 plus, solid. And the reduction is going to be E naught of copper 2 plus goes to copper, solid. And so what is zinc goes to Zn2 plus? Look on the chart. That would be plus 0.763 volts. And what's copper 2 goes to copper? Plus
0.340.
340 volts, which gives us 1.13 volts under standard conditions. And so our cell should have measured 1.13 volts. Okay, draw out the cell diagram for the next cell we did. I'll give you a few minutes to do that, and I'll be right back.